So there must be something definitely with the QFT that it's deeper than I thought. I mean, it's maybe not deeper. I don't know how to put it. It's just I think it's worth really diving into these deeper than I actually thought I would be spending time with this, because I think there's maybe some things that are relevant to learn out of that. We'll see. Just really exploring a little bit more into this. I wanted to jump into the inverse, so sorry, into the actual QFT, but then Craig actually replied. Um, uh, I was not expecting Craig to give me sort of some more steps to work on. I thought I would kind of like really try to figure out what he really meant by his answer. Like, the QFTs are similar to the inverse QFT. They only differ in the ordering of the output states. QFT equals inverse QFT times negate index mod 2 to the power of n. Um, and so the fact that he's using mod of 2 to the power of n, I think that is basically telling me there's some sort of cycling in there. So, and when I first read this, I was like, okay, so that means probably there's a certain amount of steps you can, or a certain amount of times you can apply the QFT, and that equals to the inverse QFT. But that was actually, I thought that was weird. But my point is the fact that the way the QFT is explained is like, it's gonna take you from frequency domain to the wave domain and vice versa. So you're kind of characterizing the input. You're giving it like, you're giving it a meaning, right? For me that's it's important in the sense that if I take a look at the QFT here, um, this is clearly a number, and in theory I want to be able to ignore things like what happens if there is some phase involved. Because if you take a look at these, right, I mean, this is just the decimal tool with like a 0 degrees phase. um, in the beginning I thought it I mean, sure, you can have a superposition in here, right? But what does this even mean? I mean, you can have some weird stuff like that, and that looks like some nice fancy things in here. um, but still, for me, I thought those were simply not relevant inputs. Like, that would simply not make sense at all. But if you think about it, I mean, why not? It's just that it's maybe not that clear intuitively. How can you interpret that result? How can you read that result? Um, so if I put a chance display in here, what's it gonna look like? Oh, that is fancy though. What the hell? So these gray things you see are the logarithms, so you can see the patterns better, because the actual amplitudes are really small. But that's some fancy thing in there. Wait a second. No, but it's not possible that you have, if you've got here a superposition, that you actually get some decimals in here. Those are not frequencies, right? I don't think so. Because that would mean that QFT is also its own inverse, which is not. And but I quickly wanted to test what Craig is saying here, because then it's like, okay, run these, right? Import numpy, and then so basically he creates like an array of values. Is that an ortho normal distribution? I don't know. And basically apply the Fourier transform like uh, 3 times. So he's saying like if you apply it 3 times, it's the same as applying the inverse. So I mean, instead of doing that, I'll just try to put it in. I'll just try to put it in Quirk to verify this. But there is. So what's the point? Okay, so maybe that's a question that I should answer. Like, is there a utility in using the inverse? Like, if that is the inverse QFT, is there any utility in using the in inputting an actual superposition of values? And how do those phases get affected? That would be something to. Okay, so I could probably try to scale again that down and see what happens, like I did in the other video, when I have an actual superposition of like plus 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 plus, for example. That's one thing. But before we do that, let me just quickly check, just quickly validate that. So edit circuit, because Craig really conveniently has the actual QFT and QFT, the inverse QFT. Um, so transforms to from phase frequency space. So but you see, you still define something which is an inverse, but then everyone else is calling it differently. That's my point. Um, Now, if we do something like this, right, as a QFT, and I give it like the value 2, and now I take a look at what you can see here is that it gives. So it's these, and here done with a full cycle, and then it does 2 cycles. So that's my point. I mean, it kind of feels. Uh, it's like, okay, let's see if that's true though. Like, so if I apply it 3 times, it should be the same as applying the inverse. But okay, but then I should be applying this one. Okay, it doesn't matter because what matters is that one is the inverse of the other, so it should hold regardless of that. So if I apply it 3 times, I basically get that. Um, Whereas if I do, can I do that? I think I can. I think I should be able to do that. Bam. So basically, those two things are the same. So that's kind of correct. And if I apply the inverse, or what Craig calls the inverse 3 times, and then this QFT, yeah, of course, it's the same. I mean, the behavior is the same. Okay, so it's basically, I mean, I get it. So I mean, come on. I mean, okay, but that does not answer my question, right? It's like everyone's calling what you called the QFT, everyone calls the inverse, and it's really just about namings. That's my point is that it's about the utility of the actual function. Okay, you can build one by just repeatedly applying the other. So I get it. It doesn't really technically matter, but from a usability perspective, um, and in the literature, a lot of people will say, in Shor's algorithm, we're using the inverse QFT, not the inverse, the QFT, right? So if actually Craig has also in here short period finding, so he's using actually the inverse of the QFT, which is does this make sense? So if we assume the QFT is what takes you, what gives you the frequencies, that's kind of what you want. Yeah. So you see, so that's basically you're calling it the inverse in here. But if I say Shor's algorithm. Oh, wait a second. They also use them. It's also the inverse in Wikipedia? Oh yeah, but here it's QFT. Oh, that's a mess. Come on. Okay, so there really doesn't seem to be an actual. So here is like the this diagram. It's the inverse, the first transform inverse. That's confusing. And in O'Reilly's book, what do they say? Uh, sure. Shor's factoring algorithm. I wanna see Shore. They apply the QFT, not the inverse. Okay, so might be then the other way around. Okay, I give up on this. It's just it just sucks that people don't call it the same. But I mean, actually, based on Google search images, it seems like that Craig's way of talking about it is the correct one. Okay, ResearchGate here they talk about the QFT actually, not the inverse. I mean that's probably one particular paper, not ResearchGate itself, but one particular paper. Um, here the here's the inverse, whatever. Okay, so um, but that's interesting. So that's my point here is this. There's more to these, right? So okay, so what do I wanna what do I want to explore farther? So I want to understand what happens when you um, so what happens when you so two things. First thing is what happens when you feed as an input an actual superposition, right? And that's the first question. And second question is how does the like sort of build up more intuition on the inverse QFT circuit? Like I know you can actually apply as we've seen here, you can apply these 3 times and you get the same effect as applying the inverse. But you can actually build a circuit that's basically the inverse of that. It's kind of like a mirrored version of that. And so I wanted to basically try to build that, and then step by step try to kind of see how that, you know, unwrapping, uh, wrapping of the wave into the actual frequencies. How does this look like, and whether there's some kind of intuitive stuff we can take out of that. So those 2 questions. We're probably gonna tackle only one today. I'm, okay, let's just play around with it. Okay, let's just again reduce dimensionality and play with what happens with uh, when you input an actual superposition. Can I somehow recover? I think I bookmarked it, right? So I think I should be able to basically go to my bookmarks bar QFT4. Here you go. Awesome. So, but remember that what we had here was exactly, so that was the inputs we're playing with. So now what happens? Okay, so what happens if we've got here, for example, um, the superposition plus plus plus. Okay, interesting. So you get a 0 0 0. What does these mean though? Hmm. Mm, because in theory the QFT says it transforms to and from phase frequency space. Phase frequency. So is it that okay? So I'm having sort of a thought that maybe if you give it a superposition, it basically takes a look at the actual phases, whether they're encoding anything, and it kind of does the. Could it be doing the inverse? But that would make no sense. So, because this is kind of obviously 0, 0, 0, because all the phases are like that, right? But if I would use, let's use the QFT to encode. Let's use the QFT to encode a. Sorry, let me go back to 0, 0, 0 because it's going to make it easier to then say, well, put Hanamarts in here. That's how we are gonna do it. Oh, come on. Okay, so that's how you get that. Okay, so what if we first use a QFT to encode say a wave with like a double cycle, right? So now here, if I take a look at here, what we've got is basically a superposition that actually has that 2 cycles repeated in here. Now we get rid of the Hadamars because that's already a superposition. So that was a bad idea. Okay. So that's not needed anymore. So, and now the result we get is the decimal 14. Why 14? So, but we're actually getting one number. That seems to be too much of a coincidence. So it seems to wrap if you give it an equal superposition, right? I mean, if it's not equal, like, can we make something not equal randomly like that? Okay, now we're getting 2 numbers. Okay, that's too complicated right now. So let's focus on just equal superpositions first. So as this is an equal superposition, the only thing that changes here is the phase. And for some reason that maps to the number 14. Which honestly it's 2 away from 16, which is basically the amount of states that we have in the outcome. So, and 2 is the number we've put in here. So that's a bit suspicious. So if I would put a 3, then it should go to the number 13. Yes. Ooh. So actually 16 minus that is then that's nuts. But okay. But then that is indeed. Is this what Craig meant? The QFT is very similar to the inverse QFT, only differ in the ordering of the output states. Oh, that's exactly what he means. That's exactly what he means. They only differ in the ordering. It's the QFT is equal the inverse QFT. I don't know if he means times by that, but like negate the index mod 2 to the power of n. So in our case, 2 to the power of n is 16. So minus, okay. So that would be like minus 13 mod 16, which is 3, right? Minus 13 mod 16. Yeah, of course. So that's exactly what Craig meant. That's awesome. Huh. Yeah, so technically... Okay, so technically then, you know... So it's almost like, yeah, it's very similar indeed. So if you give it an equal superposition with the phases representing an actual wave, that's what you would usually feed the inverse of the QFT. But if instead of all that, right, like we feed that to the inverse QFT, and we take a look at the amplitudes, and we forget about the rest of the circuit, right? Then we get the decimal 3. So you see, so that's and that kind of gives you directly the result you want. But if instead of that we apply and forget about the rest of the circuit here right now, like for a second, ignore all these. Okay, so and that's basically that's the difference. That's nuts. Okay, so here we've got like 13, which is like minus 13 modulo 16 is 3, and then okay, that's cool. We've learned something. um, but still, okay. So this is, but still, why? So I mean, what's the intuition here? Is it doing the same thing? Is it kind of wrapping? Because that's what I thought the QFT inverse does. But I'm gonna stop maybe talking about QFT and inverse QFT because it just feels awkward. I mean, now that it's just basically they're awfully similar, so that feels extremely awkward. So, but let's try to see what happens inside step by step here. That can be definitely interesting. Is it also wrapping? It's also, I mean, it's definitely rotations again. So, um, okay, so but basically there's some swapping going on here. What if I, what if, what if we wouldn't swap? Like, would that change anything? Oh yeah, that messes up the whole thing. Oh my, how can I swap again? Swap, 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 swap. Uh, so basically, um, how does this change after the swap? That's the first question. After the 2 swaps, it's messy. Huh. That makes it more complicated to understand. It's not even like it's totally messed up. I can't even figure out what's the pattern, like whether there's any pattern in here. But because literally this means here you'd be swapping. For example, here this shouldn't have. Okay, I see. Okay, wait a second. Oh, wait a second. Wait a second. Wait a second. So all that entire row is no, it is affected, of course. The only numbers that are not the only ones that are not affected are, of course, the ones where the swapping doesn't take any effect. But the rest is like, you know, that becomes the 1000. So that becomes this one here. Yeah. That becomes the 0, the 1010. That's gonna be tough to digest then. Here, okay, but this is okay. So this is where it starts getting interesting. So um, the first Hadamard kicks in, and it's for that for the lowest qubit, right? So for yeah, so basically these two columns, like where all is the last qubit is 1, the last qubit is 0, the last qubit is 1, right? They basically fold, kind of. Oh, wait a second. There is a pattern. So if you pay attention, if you take a look at those two halves, like, and if you take a look at each of the squares, like pairs like these, they are exactly the opposite. They are exactly the opposite, which kind of makes it just makes the beautiful effect of um, what is the beautiful effect? Beautiful effect. This is 0 and this is 180. This is like 185 and 100. If 67, 5, 112, 5. So they're literally the opposite. Um, and so when the Hadamard comes in, so why has this happened? Okay, so but that's because of the swaps in here. Because the swaps make sense to me if you think about the input being just one number. Because as I said, then the purpose of the swaps is to activate the proper controls, so the proper set of rotations are applied. So that makes intuitively sense. Now, in this scenario, I don't know how to read that yet. That's for me still a question mark. So how would you intuitively understand that? Like, is it that I start to figure out where are these things being, where the thing is coming from. So, because it definitely creates some kind of structure that is useful, because then the Hadamard basically folds those, because those are literally, if you imagine the Hadamard is applied in the last qubit, right? So if you've got like a 1 0 0 0 and 1 0 0 1, I mean, that's exactly like what you're doing. You're kind of, because that's like the common portion of the number, and that's where you're applying the Hadamard. So you're gonna fold that into either a 0 or a 1 based on the phase, on the relative phase. Like here, for example, the 0 component has 0 phase, and that component has 180 degrees. So this means it's a minus. So this means that it will fold. That makes no sense. 0 0 0, and that 0 0 0 1 has a minus. That's clearly a minus. So I mean, I'm going really low level, but I think that's the best way to approach it. So um, so the 0 0 0 0 is plus, and the 0 0 0 1 is minus, right? So if what you wanna do is you wanna take the common part out, um, then it has to have the same symbol, right? So what I mean is if you take it with a plus, mm, no, what am I saying? That's not that's correct. So it actually that's correct because it stays. It's correct because basically it falls into the entire column that has a 1, and that's because each of them has the one component has a negative, like sort of the opposite phase, like they are opposite. So effectively, it doesn't matter whether they're 0 and 180 or like this angle and this angle, they are opposite. So when they are opposite, they turn into 1, right? That's the idea exactly. So you're taking that out as is, and then you get like 0 minus 1, which after the Hadamard turns into a 1, and that's why it's in this column and not in this column. And the same happens. I have to admit the matrix representation here of that is way more useful than what I initially thought. It's way more useful than actually the IBM Q experience um, for this kind of analysis. And here the same, they're all opposite, so that's why this is folded into the column where there's a 1. In there's a 1. There's basically a 1 in the last qubit. That makes sense. Um, okay, so nevertheless, how is that swapping actually contributing to that structure? That was my first point. So first of all, of course, this is which one is this? Where is this coming from? This is 0001. So this might be the 1000. This one here. Okay, so it's like this one goes here and vice versa. Huh. Huh. Okay, this one goes here and vice versa. Okay, I get it. This one stays. This one is basically it's this one. Yeah. This one is this one. Okay. And then that kind of so 0101 would be 1010. Okay, so here these diagonal elements get exchanged. So this one goes with this one, and I would assume that those are the ones that stay the same. Yeah, it's super interesting. So that's the structure, and this one gets exchanged with, sorry for the mic, with this one, and this one with this one. Interesting. But what's the intuitive, like why? this has to do with, so as I said, when it's just a number, the input, then it makes total sense because you're basically activating the the, the proper controls. Here it seems like you're shuffling things so you can fold appropriately. But now in in the inverse QFT, like if I would apply the proper inverse QFT, right, that swap happens at the very end because you're kind of mirroring that thing. So and I believe it's a bit more intuitive the because then the actual because the actual circuit can be read in a nicer way where you're like, okay, you're kind of first you're like folding your you're folding your phase values and in a way that they get to a nice number, and then you just flip the things at the end. And probably no, I thought if you would flip those beats that you would get a 3, but that makes no sense. That's not what's happening. Okay, but there is indeed here. Okay, so this is what happens. Now, now the next piece, the next part is the control S, which this means in this case because all the available amplitudes, they all have a 1. Oh no, sorry, they don't all have a 1. Because now the control is the second qubit from the right. So this doesn't, this doesn't, this doesn't, this doesn't. And so this column will stay the same, and this they all probably have. Yeah. And so you're, okay, I see what's happening. So here intuitively those rotations, they just make your, they just, they really fold your superposition, so that then the Hadamard can, the rotations prepare the superposition so the Hadamard can properly fold them. That's pretty neat. So that's basically gonna prepare it this way. So now when the Hadamard comes in here in the second qubit, so that's exactly what you have here, because the second qubit from the right is a 0 and here is a 1. So it's really the perfect, it's kind of the perfect spot. Yeah, that's exactly where you should apply it to really fold that into one column. And now because they all these pairs they all have the same phase, that's gonna fall into the 0 column. So that's gonna go, where's it gonna go? Is it gonna stay here? I think it's simply gonna stay here after the Hadamard. Yeah. You see? Cool. Nice. Neat, 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 neat. And then the same is gonna happen here. So this is gonna prepare. Remember the Hadamard is the one. The Hadamards are the actual things that fold in this case. So, and this is gonna apply the third qubit from the right, second from the left, and so it's a 0, it's a 1, it's a 0, and it's a 1. So that's basically gonna pack these into one value and these into another value, right? So obviously what the S and the T are going to do, it's they're going to prepare those phases on the one component, because this is the control, so this means it's going, that's pretty cool. That's pretty cool, man. And that's the one component, so it's gonna It's gonna touch the face in here with an S and a T. With an S and a T? No. Wait. Ah. So those are gonna be touched by the S. Definitely. But then the T is gonna touch the, it's gonna rotate these, 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 all of them. Okay, so the T is gonna be applied to the entire column. And I can probably separate that as I did. Let me clean that out because this is a bit messy here now, just so we can see this. I'm gonna separate those operations. So we're gonna first do an S and then we're gonna do a T. Just so we see it. So the S did it rotate anything? Why it didn't? What is an S actually? What is the S? Is the S the root of Z? So it's like 90 degrees. I thought this would actually, there where the third qubit from the right is a 1, for example here, right? Or am I again reading the numbers wrong? Of course I'm reading the numbers wrong. That's the second from the right. Oh my god. But I think my previous explanations made sense anyway, right? This is applying a rotation where that doesn't make any sense. This should be this is correct. I mean, come on. The control is on the second qubit from the right in here. Yeah, of course. So that should be on the third. Oh. Yeah, but it should rotate this one. And it doesn't. This shouldn't be rotated. But of course it doesn't, because again it only rotates if both are 1. Of course, because it's like the root of the Z, so that doesn't apply anywhere. Doesn't apply anywhere. But still, intuitively, it's like I'm just following the algorithm, and you know, you see it evolve, and yeah, it makes sense. But like intuitively, how are you describing that intuitively at all? I mean, this is a bit buggy. So if I now, so the S doesn't get applied really. So if I do this here, okay, now you get the T's where you want them to have, and exactly your now the Hadamard is going to pack these into a 1 and this into another 1, right? So basically this is going to stay here and this is going to stay here, because that's where the 1 component is. They're going to stay here and here after the Hadamard. So if I copy that and I put it after the Hadamard, bam, that's what you have. And the same story here, right? So Jesus, just disappear from my screen. basically, basically, this is gonna, this rotation is gonna apply if there's a 1-1 here, which there is. If there's a 1-1, which there's not, and a 1-1, which is also not. There is here. So that actually rotation also happens. Because if that didn't happen, yep. But if the T does, if you take the T, nothing changes. But if you take that, there's like a little rotation that is missing, right? So that's what's. So this is happening, taking place. This is being executed. This is being executed. Um, and then of course I'll just move that. So you see the final effect is the Haruman wraps it up. Why did I move it if I already have it here? I don't know. Here I want to move. Yeah. So that's what we see with the phases being opposite, and then yeah. So that's it. But still, I can't really tell what's the intuition in here. The swaps seem to prepare the structure. Maybe there's just no intuition. It's just the way this works. It's just the way you're encoding a mathematical function here. It's just not intuitive. It's just maybe mathematically makes sense, but this is not intuitive. Because what does 13 mean anyway? I mean, yeah, sure. It's like minus, if you minus it and then do modulo 16, that's the frequency. But then it's I think more intuitive to actually take a look at the inverse circuit, not at this circuit this way. So this is, but this is definitely really interesting to see that basically they are both extremely similar. So I've applied a QFT to a 3, right, to get that superposition. Then we've run another QFT to basically get that here. So but it's still not the inverse. If I would now apply, let me get rid of all the stuff in here that is just cluttering the screen. So all the measurements gone. So if now I would apply another QFT, right? So I've got basically 4 QFTs here, 3 QFTs here, would be the same that applying the inverse QFT to that particular input, right? But that's then another question. So what does it mean to apply the inverse QFT when you give it an actual frequency number? It shouldn't really mean anything. But it seems like there's something going on. I don't know. 3 times. What if it's a 2? Well, wait a second. So I have to apply a QFT. So I get. So it's kind of the. So you're kind of getting the same, but it seems to be rotating the opposite way. Or is it kind of rotating 14 times? You see, it seems like those things are kind of mirrored, right? it's like this seems to be rotating counterclockwise, this seems to be rotating clockwise. Like da 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 da, and then bam, and then you've got 2 full rotations. Really? So this means if I basically clear all the stuff, I'm gonna put the number 3 in here. I'm gonna apply the QFT. Like this. So I'm getting that superposition, which is that wave encoded like that. So you're telling me that if I apply the inverse to that, let's say we're doing this 4, and I apply here also the input number 3, and we're taking now a look, forget about this monster here, so we're taking a look at this. So literally it's the same thing, but it's like this seems to be rotating counterclockwise and this seems to be rotating clockwise, which intuitively makes a bit of sense because you're talking about the inverse, right? So you're talking about the inverse of the operation. But that's okay. It's pretty cool. I'm learning quite some stuff. So basically, because those were kind of missing pieces in terms of okay, what happens? Because again, it's a matter of definitions, right? So the QFT is defined as in like you give it a or the way I thought is like the QFT is like you give it a frequency and it just generates the wave, right? In the phase in the phase domain, so to say, uh, in the phase of your final system state. And so, but if you want to do the opposite, you should use the inverse of the QFT because basically the inverse is rotating counterclock. Ah, so it's kind of like winding the clock backwards. Kind of. Of course. Of course. It's basically... so it's basically... Oh, wait a second. Is it like this? So is it... So if you are using the... If you're using the inverse, it's just basically rotating the other way around. So if you're saying, and I'm talking about intuitive rotations, is like you're unfolding, right? If you give a number to what Craig calls the QFT, if you give it a 3, it's gonna do the counterclockwise unfolding until you get the actual wave. Counterclockwise. If now I apply a QFT intuitively, it should wind the thing clockwise and end up with a 3. Yeah. With a 2, sorry. All the time here is a 2. Because now the QFT, the inverse is... and so... And if you're applying... So if you're giving a 3... a 2 to the inverse of the QFT, it's gonna do the same like the QFT, but it's just gonna do it clockwise. And so if you apply the QFT, yeah, then you're gonna get the same. Oh, okay. So that's the difference. That is the difference. Yeah. So it's really, if you intuitively think about the quantum Fourier transform as this kind of folding and unfolding, then it's just a matter of are you gonna do it clockwise or counterclockwise? Huh? And so that makes then the distinction not necessary, right? Because it's just a matter of taste, or it's just a matter of like design. So how do you design your circuit? So basically, I mean, it does make a difference. Like, can you have like, does make a difference, right? Because for example, for phase estimation, for sure, like for Shor's algorithm and the phase estimation, it's like um, it really depends on how how is the how do you interpret the superposition that's generated by the modular exponentiation part of the algorithm. Yeah, because that's going to define whether you should use the QFT or the QFT inverse. Because if I were to use the QFT here, it would basically mess up. I mean, it would not mess up. It would just give me that. It would just give me that 14, right? Basically, because what I'm trying to do is instead of winding the clock the other way around, I keep doing it counterclockwise. So that's interesting. So it does give me the same result, but like on on the other side of the box, right? Maybe I should do a bit of more thinking about this, but I think I can leave the video here for now. So, oh man, that's interesting. So now I think I understand at an intuitive level what happens when you're playing with single numbers and equal superpositions with waves encoded in the phase of those superpositions. Um, waves, I mean the data, right? Uh, and what happens when you give them as an input to QFT or QFT inverse. So the intuition here is, the one turns clockwise, the other one falls clockwise and falls counterclockwise. And if you give it an equal superposition, it's gonna fold it up. If you give it a single number, it's gonna unfold it. So that's what it does, and that's because of the Hadamard's. That's basically because of the way it's built with the Hadamard's and the rotations, right? So that's the effect it's gonna have. It's gonna either fold it if you've got it unfolded, or yeah, that's pretty nice. That's super neat. Now there is indeed, so there's two questions that I still want to touch here. So one is, so what's an actual circuit for the counterclock, for the clockwise, so for the QFT inverse from Craig here. And another one is, what happens if you don't give it an equal superposition? That's definitely sort of the missing piece, right? So what happens if the input is not an equal superposition? Well, in theory, if it's not an equal superposition, it should be the same as in, like, it's the case like you give it a number, so instead of giving it like a 2, if you give them an not equal superposition, you can probably assume that you're giving it like multiple frequencies, so it should create the combined wave. So I think that's the and that's actually yeah, so that's probably what's gonna happen. Yeah, but I'll do another video on this. So to deep dive into this, because that's exactly the case that you wanna. It's not the perfect case, right? Because those are edge cases, right? Like when you really have the perfect wave here encoded, and then it's giving you back like a 2. I said, like, that's a pure frequency. It's a wave with a pure frequency 2. Um, but in reality, you're gonna have a messy wave. So you're gonna have here a not an equal superposition of all the different possible frequencies and their contribution to the wave. And so, yeah, but it's basically wrapping up. It's like folding and unfolding. That's all it is. That's all. That's all it is. I don't know. I still feel it's just maybe I'm just missing something here. I still would like to. I'll definitely take a look at the actual circuit of the inverse QFT to see how that plays around um, with basically the swabs at the end, and then the controls and the rotations being different, I guess, and see what's the intuition under the hood there. But basically, that's it. It's yeah, I'm still not really happy, but there's definitely something here that's been interesting. The kind of clockwise and clockwise. That's definitely cool. Cool.